so section 6.5 is hopefully a friendly section. This is just a section from my intermediate algebra class. I think I just copied and pasted all the problems and just changed the section number as much as anything. I don't think there is a single problem in this section that is new to college algebra. So hopefully everything on here feels like a review. The beginning and the ending problems are problems that are just completely review problems. I'm going to do those first, and then the middle banks of problems are new for the semester that we haven't done anything like, and I'll need to do a little bit of a review before we do those. But the first 12 problems we can do theoretically without having to yank our calculator out. So each of the first 12 problems have a logarithm. I don't see any letters, which means I can get a numerical value for these logarithms. And the hopes are you don't have to rely on your calculator. So problem 2 is asking the question, 3 to what power is 9 squared? Because every logarithm asks the question, the base to what power is the argument. In this logarithm, the 3 is the base, the 9 squared is the argument. If I wanted to solve this without my calculator, then I'd need to rewrite the 9, which is 3 times 3, as 3 squared. And if I'm going to write the 9 as 3 squared, I'm going to get two exponents next to each other. So instead of writing 3 squared squared without a parentheses, I'll do that rather than writing 3 squared squared. Although it's not wrong to write that, it looks odd to write it without the parentheses. Now I'm in the position where I have one base 3 and two exponents that apply to it. That's the situation where you should multiply exponents. I have each side written with the same base, so I can get my answer by dropping the bases and equating the exponents. So the answer to this problem is going to be 4. It's not really x equal to 4 because there's no x in the problem that's written. This logarithm is just equal to 4. If you're going on to calculus, this is the kind of math that you should just be able to do just without having to really struggle, because there's a lot of messy algebra in calculus, and this is in some sense basic math that you should just be able to do. For this class purposes, if you can't do this, it's not going to be the end of the world. It'd be okay if you did this. If you did log of 9 up arrow squared divided by log of 3, and your calculator would tell you that this answer is still 4. So the answer to this is 4 with or without your calculator. Prefer you doing this without your calculator, but you should check with your calculator anyways. Number 4 is asking the question, the base 7 to what power is 1? And the answer to that question is 0, because anything to the 0 power is 1. So the answer to question 4 is just the number 0. And just like I could have done number 2 without knowing anything about logarithms, just with only having the ability to press buttons on my calculator, I could do this as well. To do this on my calculator, I would do log of 1 divided by log of 7. If you do log of 1 divided by log of 7, it tells you that it's 0 as well. So for each of the first 12 problems, they're possible to do without a calculator, maybe easier to do with a calculator. But anytime a logarithm simplifies to be an integer, there's definitely a strategy that can be used to solve that particular logarithm without breaking out a calculator. 6, the question it's asking is 6 to what power is 216? And if you know the answer to that question, then you don't need to pull your calculator out. If you don't know the answer to that question, then your calculator is maybe the only way you can do it. But because powers of 6, they're not as commonly known, but it turns out that 6 to the 3rd power is 216. 6 times 6 times 6 is 216. So the answer to problem 6 is just the number 3. And then similarly, if I didn't know the question that the logarithm was asking, or if I knew the question but I didn't know the answer to the question, then I could do log of 216 divided by log of 6, and I'd get 3. Turns out that this side angle, maybe it's kind of hard to read, but at least you could see everything. So the answer to that is 3 one way or another. To do 8 with my calculator, this shorthand is okay. To do 8 without my calculator, the shorthand notation for the logarithm probably isn't that helpful. And I know that the ln can always be replaced with log base e. And for using my calculator, the ln notation is probably preferred. For trying to figure out what this logarithm is equal to without my calculator, the equivalent log base e is better than ln. So problem 8, the question that it is asking is e to what power is e to the 4th? And the answer to that is 4, because e to the 4th power is e to the 4th. So my answer to this is going to be 4. This is a friendly calculator one, because my calculator has an ln button. I'm able to do this on my calculator without having to hit a divide. So this on my calculator, I would do the ln button, and then I'd hit second and ln, and then up arrow 4. So that is the ln of e to the 4th, parentheses, parentheses, and it tells me the answer is 4. (10) and 12 should be similar problems, something that can be done without a calculator. 10 again would be very easy to do with my calculator. If I'm doing 10 without a calculator, that ln notation isn't helpful. So I'm going to replace ln with log base e. They mean the same thing, natural log and log base e. ln and log base e are just different representations for the same meaning, that have the same meaning. The question that's implied in number 10 is the base e to what power is 1. The answer to this is 0, because anything to the 0 power is 1. So the answer to number 10 is going to be 0, and it's not really x equals 0 because the initial problem doesn't have an x in it. And again, on my calculator, ln's are easy. I would just type ln 1, close out my parentheses, and if I just entered that on my calculator and hit enter, it's going to tell me it's 0. The last even one in this grouping would be tricky to do without a calculator. It's similar to, I think, the first one. The last one is number 12 is asking the question, the base 5 to what power is 25 squared? And just like I did with the 9 in the earlier problem, the 25 can be written as 5 times 5, which is 5 squared. So I can rewrite the right-hand side as 5 squared. Again, I could have written the right-hand side as 5 squared, but that looks odd to have two exponents like touching like that without some sort of parentheses. So I put the 25, wrote it as 5 squared in a parentheses. I'm going to multiply these exponents. This is going to give me 5 to the x equals 5 to the 4th. And for those two sides to be equal, that x has to be 4, so the answer to this is going to be 4. Again, I can do this mindlessly on my calculator, doing the log of 25 squared divided by the log of 5. So if I did log of 25 squared, using the square key if I want to, divided by log of 5, it's going to tell me that the answer is 4, just as well as had I done it, just like I did by hand. So the first 12 problems, it would be really nice, especially if you're going to calculus, to be able to do all of these problems without having to pick up your calculator. But if you're not at that point yet, it's okay. There won't be enough points on the test for this to really impact your grade, that if you're presented with a problem like this on the test, if you use your calculator, I'll be content with that, because it's really going to be an insignificant part of the test. So it's not going to, if you have to use your calculator to do this, it's not such a big deal. I'm going out of order a little bit. I'm going to the bottom problems now, just because this is also review. We've done this kind of stuff already. We've used our calculator to evaluate logarithms, and this says rounded 2 decimals. So each one of these logarithms, well, at least 38, 40, and 44, are going to have a nasty decimal equivalence. And those I couldn't do by hand. So none of the, well, 42 I could actually do by hand, I think. But in general, most of these, 3 of these 4 problems, I couldn't do. I could make a guess as to what the answer to 38 is. 38 is asking the question, 7 to what power is 14? The answer is not 2. The 2 is not the answer, because it's not true that 7 squared is 14. It's actually true that 7 squared is 49. So the answer isn't 2. It's actually some number that's bigger than 1, because 7 to the first power is less than 14, and less than 2, because 7 to the second power is 49. And the best way to get this, the only way I can get this right now, is just to use my calculator. I'll go log of 14 divided by log of 7. And my calculator tells me it's 1.356. I'm asked to round to 2 decimal places. So the answer should be, I'm going to write 1.36 for my answer to this. And it should be the case that 7 to the 1.36 power is about 14. If I wanted to check this, the question that's being asked is 7 to what power is 14. I'm saying it's 1.36, which means if I break out my calculator and go 7 up arrow 1.36 power, if I could actually do that right, 7 up arrow 1.36 power, I should get something close to 14. It's not going to be exactly 14 because it's a rounded answer, but 7 to the 1.36 power is 14.103, which is close to 14. If I wrote 7 up arrow and did 1.356 power, which is a less rounded version of the answer, I get closer to 14, 13.99. So the more decimals I take in the expansion of log of 14 divided by log of 7. So if I did like 7 up arrow 1.356207187, I get exactly 14 on my calculator. So the more decimals you carry in your checking, the more close your checking is going to get to 14. But that doesn't really need to be done. For 40, it's asking the question 9 to what power is 36, and then 4 is not the answer, because 9 to the 4th power, it doesn't equal 36. 9 to the 4th power is a pretty large number. 9 to the 4th power is 6,561. So if you said the answer is 4, then you're saying 6,561 equals to 36, because the question that's being asked is 9 to what power is 36, and 9 to the 4th power is not 36, so that isn't the answer. Again, I know that the answer is a number bigger than 1 because 9 to the 1st power is 9, less than 2 because 9 to the 2nd power is 81, but I don't really know what the answer is, so I'm just going to go log of 36 divided by log of 9, and I get 1.6309. I'm asked to round to 2 decimal places, so I only need to see 3 decimal places. The 3rd decimal being a 0 tells me I don't need to round up, and for my answer to this problem, I'm just going to write 1.63. And again, that's a rounded answer. It's good enough, but it's not the exact answer. Even the answer that my calculator gives me that has those 9 or 10 decimals is still an approximate answer. If I had a calculator that carried more decimals, or I had a computer program, there are infinitely many decimals in this answer, and the decimal expansion doesn't have any patterns and it doesn't repeat. It just goes on forever. These are irrational numbers. 42 I put in this section because I didn't think most of you could do it by hand, but it actually is doable by hand. The question that this is asking is 2 to what power? 2 to the x power equals 0.25. If you're ultra clever, you could get this without your calculator, and it would be very impressive if you're, going to be an A calculus student. This is the kind of thing that you need to be able to pull out of the air at some point. So if you took a second and tried this, it would be cool if you got the right answer. This could be done like this. 0.25 is the same as a quarter. And I know that 2 to the negative 2 power is a quarter because 2 to the negative 2 power is 1 over 2 squared. The answer to this is going to be negative 2. And I'm not going to be surprised when my calculator tells me this is a negative 2. But I put this in the calculator only section because this is a skill that I wouldn't imagine most people would have. To be able to know that that decimal is equal to that fraction, and to know that this is equal to a negative exponent. There's like two skills that aren't generally good skills for students. So my calculator, if I did log of 0.25 divided by log of 2, it's going to give me the answer of negative 2. But then again, I could have got it by hand. Anytime I use my calculator to evaluate a logarithm and the answer is an integer, that means there's a way, if I'm clever enough, to do it without my calculator. The last problem, I'm just going to do it on my calculator. I'm going to go log of 7 divided by log of 6. There isn't any kind of intuitively wrong answer because, like in 40, 9 times 4 is 36. In 38, 7 times 2 is 14. So it's tempting to write. In 38, it might have been tempting to write 2. In 40, it might have been tempting to write 4. There probably isn't any real temptation in 44 to write a wrong answer. So I'm just going to go log of 7 divided by log of 6. And I get 1.0860. And I'm only asked to round to 2 decimal places, so I only really need to go to that 6. That 6 tells me to round that 8 up to a 9. And the answer I'm going to write for number 44 is 1.09, which means 6 to the 1.09 power is close to 7. That's what this means, that the answer is the power that I could raise 6 to get something close to 7. If I did 6 up arrow 1.09, I should get something close to 7. I got 7.049, which is close. It's not maybe close enough, but it's close. But because it's only a 2 decimal rounded answer, the checking doesn't come out that good, but it comes out close. So that's all old stuff. There's new stuff that's new for us this semester, but not new in terms of you should have seen it before. But before I get to the new banks of problems, I need to review a little bit. 3 rules of logarithms. And the rules are bi-directional rules, which means they work forwards and backwards. And I'll pull out my cheap calculator to just illustrate the rules because my cheap calculator makes it easier to do logarithms. I give the rules names. One rule I call the power to product rule, or power to multiply rule. I don't know why I call it power to product. You might want to think of this as exponent to multiply. That would have the same meaning. Generically, that rule says this: if I have the log of any base of anything to some power, that power, the exponent, can be brought out in front of the logarithm and multiplied by the logarithm, and you'll get the same result. So and I'll do something that's more concrete. So it would say this, that the log base 2 of 25, whoops, I want something better than that, would say the log base 2 of 8 to the 6th power. Let me figure out what that is. I'll use this calculator to do that because this calculator does logarithms so nice. So logarithm base 2 of 8 up arrow 6th power, it says that if I do find out what this logarithm is equal to, which is 18, so this logarithm is equal to 18, the power to product rule, or the exponent to multiplier rule, says if inside a logarithm I have an exponent, I can produce a logarithm that has the same, it simplifies to the same number if I brought the exponent and multiply it by the logarithm. So if I write 6 times, and I don't need a times symbol here, I'm just going to write a 6 in the log base 2 of 8, it says that these two are the same. This is the exponent, and this is really the multiplication, because this is really 6 times the log base 2 of 8. And I'll show you that both of these are 18 mindlessly on my calculator. I'm going to go 6, and then I'll hit my times key, but I don't really need the times. Then hit my log button, and then log base 2 of 8. And I get 18 that way. So the power to product rule, which you could call exponent to multiply, says that if a logarithm has an exponent, that you can make that exponent, you can calculate the logarithm the way it sits, or you can make that exponent a coefficient and find the logarithm and then multiply by that exponent, and you'll get the same result. And it's bidirectional, which says this: if I have something like this, 3 times the log base 5 of 625, that if I have a multiplication, a number multiplied in front of a logarithm, that I can figure out what this is. And let me figure out what this is on this easy calculator. Going 3 times, hit my log button, log base 5 of 625. It says, so this equals to 12. It says I could do with that 3, I can move that 3 inside the logarithm and make it an exponent, because this is a multiply, and I can go multiply to exponent. It says that this logarithm, the log base 5 of 625 cubed, is also going to equal 12. So the power to product rule, or the exponent to multiplier rule if you prefer, is a bidirectional rule, and it tells me that these two logarithms are equal, and I'll show you that. If I do the log base 5 of 625 up arrow cubed, see that perfectly? That also equals to 12. So that's the first of 3 logarithm rules that we have to remember. Generically, that says that if I have this logarithm, like if I have the log base 3 of x to the 5th, that's going to be the same as 5 times the log base 3 of x. Even though I couldn't do either of these on my calculator, the rule says that these are equal. Similarly, it would say something like 7 times the log base 2 of y equals the log base 2 of y to the 7th. Basically, this rule says that if inside a logarithm I have an exponent, I can move that exponent and make it a coefficient and multiply it by the logarithm. I can take an exponent in and outside of a logarithm. And if there's a number in front of a logarithm, that number being multiplied by a logarithm, that number can be brought inside the logarithm if you make it an exponent. And similarly, if there's an exponent inside a logarithm, I could bring it in front of the logarithm and make it a multiplication. So of the 3 rules, that's in some sense, the simplest rule, because I'm just moving one number, and I'm not getting more than one log. The next rules involve multiple logs, either making 2 logs into 1 log or 1 log into 2 logs. And those rules are how about the add to multiply rule would be one of the next 2 rules that we need. And the add to multiply rule formally says this: if I have 2 logarithms and they're the same base, that I could calculate each of the logarithms individually and add the results, or I can find one logarithm that has the same result if I multiply the arguments. The adding part of this formula is that plus sign. The multiply part of this formula is the multiplication of x times y. Let me show you in practical what this rule says. This rule would say that this logarithm, the log base 2 of 8 plus the log base 2 of 4 equals, the rule says if I have two logarithms separated by a plus sign, that's going to equal one logarithm, same base, with the arguments multiplied. So this log base 2 of 8 plus the log base 2 of 4 is the log base 2 of 8 times 4. If I just change the b to 2 and the x and the y to 8 and 4, and of course it's not that hard to multiply the 8 and 4. So I'm going to show you that this is true. So it's supposed to be the case that if I compute the first log, get a number for it. So let me do that. Log base 2 of 8 equals to 3. And then if I do the second log, which is a log base 2 of 4, which equals to 2. So if I do the two logs separately and add the results, I get a 5. The rule says that that logarithm there should also equal 5. So if I do the log base 2 of 32, I should also get 5. And I do. So the rule works. It's a bidirectional rule as well. That rule would say this: if I had the log base 6 of 216 times 36, that would equal the log base 6 of 216 plus the log base 6 of 36. So it works. Oh, this is supposed to be multiply. It's supposed to multiply. So that this is also supposed to be a true statement. If I do this logarithm, the logarithm base 6 of 216 times 36, which is equal to 5 again. It's supposed to be the case that if I can do these two logs separately, do the log base 6 of 216, which is 3, plus the log base 6 of 36, which is 2, that I get the same. I get a true statement. So the add to multiply rule is a bidirectional rule. It says if you have two logarithms separated by a plus sign and the logarithms are the same base, that you can compute the values of the logs separately, add the results, or you can get the same result with one logarithm if that one logarithm has the same base and its argument is the product of the arguments. And generically, if I had something like this, so when we get into the text, if I had something like this, the log base b of x to the 5th, or the log base 2 of x to the 5th, plus the log base 2 of y cubed, this rule applies to this. I couldn't check this on my calculator, but this rule would say that this equals the log base 2 of x to the 5th y cubed, because I have two logarithms, same base, plus between. Anytime that's the case, you can get one logarithm that has the same value as the original expression if you write one logarithm, keep the base the same, and multiply the arguments. Similarly, this rule works backwards. If I had something like this, the log base 7 of x to the 4th y, that's one logarithm that has a multiplication. This rule says that that logarithm would be the same as the logarithm base 7 of x to the 4th plus the log base 7 of y. So it's a multi-directional rule. Add to multiply, multiply to add. This is an example of using the add to multiply portion, as is that's using add to multiply. And these are using multiply to add, multiply to add. The last rule that we need is the divide to subtract rule, or subtract to divide rule, depending on how you write it. There isn't a right or wrong way to say it or write it. So the last rule is the, I'll say, subtract to divide rule. And formally, it says if you have two logarithms, same base, separated by a minus sign, there's the subtract part, that those two logarithms can be computed individually and the results subtracted, or you can make one logarithm with the argument, the quotient of the two arguments, and it's going to have the same result. Let me show you with an application of this. If I had something like this, the log base 2 of 128 minus the log base 2 of 16. This rule says that I can compute these two logs separately, and let me do that real quickly. Log base 2 of 28 of 128. Log base 2 of 128 is 7 minus, and then log base 2 of 16 is 4. So this original problem was equal to 3. This subtract to divide rule says I can produce one logarithm that's equal to 3, and that logarithm is going to be the log base 2 of 128 over 16. Let me just divide 128 over 16 real quick. 128 divided by 16 is 8. So that says that this logarithm, the log base 2 of 8, is equal to 3. So that one logarithm has the same equivalence to calculating two logarithms separately and subtracting the numbers. So if I did this, log base 2 of 8, 8 is 128 divided by 16. Log base 2 of 8, I actually could do that, just clear log base 2 of 8, that does equal to 3. So it works that way, and it works backwards. If I had something like this, the log base 3 of 243 over 9, the rule would say I can do this logarithm. So if I did this, the logarithm, the logarithm base 3 of 243 divided by 9, which is equal to 3, it says that I could, if I have a logarithm with a division, expand that one logarithm into two logarithms, separate the logarithms by subtraction, keep the base the same, split the arguments. So it says if I do these two logarithms separately, specifically if I do the logarithm base 3 of 243, dying on my calculator here, logarithm base 3 of 243, this one comes out to 5. The next one, if I do logarithm base 3 of 9, that one comes out to 2. It says if I take those two logarithms and subtract them, I'm going to get the same result as the original problem. In more practical purposes, like when we get to the homework, if I had something like this, the log base 2 of x to the 8th minus the log base 2 of y to the 6th, that's equivalent to the log base 2 of x to the 8th over y to the 6th. That would be how I would wind up applying this rule when we get into logarithms that don't have numbers that I could use on my calculator. Similarly, if I had something like this, the log base 9 of x to the 4th over z, that's going to equal to the log base 9 of x to the 4th minus the log base 9 of z. So theoretically, those three rules, the multiply to, the add to multiply, the subtract to divide, the multiply to exponent or exponent to multiplier rule, were all rules that you've seen either in a recent high school course or in intermediate algebra. And I just wanted to make sure you're familiar with those rules before we get into the section, the homework problems in the section. And then the homework problems in the section all involve rewriting logarithms using the rules that we just presented. And for each of the problems, I usually shortcut, but I will not shortcut the first problem in the 13 through 24, and then I'll probably shortcut the rest of them because in reality, these rules are, it's nice to know the rules formally, but in reality, we usually kind of do something that's equivalent to using the rules without formally using them when we solve problems. So problems 13 through 24 in this section says expand into sums and differences of logarithms. Basically, I want to take a problem that has one logarithm and write something that's equal that has as many logarithms as the problem has letters. So I want to, here, my goal is to write an expression, in this case, that has 3 logarithms, right, logs, that's equal to the original problem. So the expand, I start with one logarithm. I want to expand it to more than one logarithm. I know by how many logarithms I want to expand it to based on the number of letters that are in the problem. And this has 3 letters, so I want to expand it into 3 logarithms. So my goal in my answer is to write something that's equal to the original problem that has 3 logarithms, 1 for each letter in the problem. The first thing I'm going to use to expand this is the multiply to add rule. And I'm going to do an extension of that rule because the rule that I showed said that if you have a logarithm that has multiplication, which this does, it has x times y cubed times z to the 5th. What I showed that is if you had 2 things being multiplied, you could break one logarithm into 2 logarithms if you add the arguments, because multiply to add. That rule can be expanded, and I'm going to use the multiply to add rule, and I'm going to create 3 logarithms, 1 for each letter, and between the logarithms, I'm going to put plus signs because this is really x times y cubed times z to the 5th. The multiply to add rule extends to more than one multiplication inside a logarithm. The multiply to add rule generically says if inside a logarithm I have multiplication, that I could expand that logarithm into multiple logarithms as long as I separate each of the logarithms by a plus sign. That's the first part of my expanding. This second little parenthetical comment, express powers as factors, it means make any exponent into a multiplication, or it wants me to use the product to power rule. It wants me, that parenthetical comment wants me to make any exponent inside a logarithm a multiplication or a coefficient. So the proper expansion, or the answer for problem 14 that's preferred, is rewriting this as a log base 4 of x plus 3 times the log base 4 of y plus 5 times the log base 4 of z. And that's all there's to do. Unfortunately, it's kind of hard to check. I guess if you knew how to go backwards, apply the rules in reverse, it would go back to the original problem. But there isn't a real slick way to check. It's not like I'm going to pull my calculator out and check because of the letters. So that's all that there was to do for 14. Let me jump to 16. So if I was doing 16 and I was being very, very efficient or inefficient, and I'll use the rules exactly how they're written, the first thing I'm going to use is the divide to subtract rule. The divide to subtract rule says that if inside a logarithm I have a division, that I can take that one logarithm and make it into two logarithms if between the two logarithms I put a subtraction and I put the argument or the numerator as the first argument, the denominator as the second argument. So I've used the divide to subtract rule to expand. I've expanded it into two logarithms because the problem only had two letters. I only wanted to expand it into two logarithms. And now I'm going to use the power to product rule or the exponent to multiplier rule to get the answer that's desired here. So the answer that's desired is 4 times the log base b of x minus the log base b of y. This expression is equal to the original problem, but it looks different. It's expanded into multiple logarithms. 18's a bit tricky. And 18, if I shorthanded it, it probably wouldn't be so tricky. Let me do it longhand and then tell you how I would shortcut it. So in this problem, I ultimately want to go from 1 logarithm to 3 logarithms. And to do it properly, well, let me do this. 18 vs. I'm going to do these two problems on the same sheet. These two problems can't possibly have the same answer because they're not equal to each other. For their expansions, for two logarithms to have the same expansion, they have to be equal to start. So the expansion for problem 18 can't be equal to the expansion for this problem. This is a new problem with a different answer. A new but similar problem. It's not problem 18. Let me do this one, which is easier. I'm going to expand this using the divide to subtract rule. The divide to subtract rule says if I have a logarithm and that logarithm has a division, that I can make that one logarithm into two logarithms if I separate the logarithms with the subtraction, put the numerator as the first argument, the denominator as the second argument. So here I use the divide to subtract rule. Now I'm going to use the multiply to add rule and make this the log base 7 of x plus the log base 7 of y minus, and then I'm going to use the exponent to multiply rule minus 3 times the log base 7 of z. So this is the answer to this. That is the proper way to expand this into 3 logarithms. If I have exactly the same answer when I do the real problem 18, then I've gone wrong somewheres. And where I've gone wrong is probably with the y. So to do this properly longhand is a nuisance, but I'll do the same thing. I'm going to use the divide to minus rule. And then I'm going to use the multiply to plus rule. The big trick in this one, if you're forcing your answer that this minus right here, or this second logarithm doesn't want to break into 2 logarithms, I technically should bracket it or put it in a parentheses. When I expand this logarithm, that minus sign is going to attach to both logarithms that I expanded to. So because the denominator is going to lead to something that could be expanded, I should probably have it in a bracket. And then when I expand that denominator using the multiply to add rule, I can get a proper sign. Now I'm going to distribute the minus, attach the minus to the y and the minus to the z, and get this. Log base 7 of x minus log base 7 of y minus log base 7 of z cubed. The difference between my answers for the new problem and the answer to this problem is the sign in front of the y, which is good because that's the difference between these two problems. In general, if I'm asked to expand one logarithm into multiple logarithms, I don't use the rules one at a time. I go directly from the problem to the answer, and let me show you how to do that by making some problems up that aren't in the text. And so what I've done so far is the proper way to do the problems, but not really the way that people do the problems. So these are just extra problems to show you how to expand quickly. If I gave you this, log base 2 of x, y to the 4th, zw. Let me do that one first. This one, if I want to expand it, I need to make 4 logarithms. 1 logarithm for the x, 1 logarithm for the y, 1 logarithm for the z, and 1 logarithm for the w. Immediately, the only logarithm that's going to have a number in front of it is the y, and it's going to have a 4 in front of its logarithm because I would have had a y to the 4th here if I put the y with its exponent, and I was going to make that 4 into a multiplication. So I wrote 1 logarithm for each letter. I made the exponent into a multiplication, and now I'm going to insert my signs. Basically, any letter that's in the denominator, when you're doing the shorthand, gets a minus in front. And everything else is going to get no sign or plus. So when I go to put the signs in, both the z and the w are in the denominator of the fraction, so they're going to pick up a minus in front of them. The first logarithm never gets a sign, and then any other logarithm, since the letter's not in the denominator, gets a plus. So that would be the speed expansion, using the rules of logarithms, but using them slickly. If I gave you something like this, the log base b of x to the 6th over y to the 4th zw. If I want to write this and expand it, because it has 4 letters, I'm going to make 1 logarithm for each letter. I'd get the log base b of x for one of my logarithms, the log base b of y for a second logarithm, the log base b of z for a third, and the log base b of w for a 4th. I'd make the exponents into coefficients. Instead of writing an x to the 6th and moving the 6 out front, I'll write the 6 out front. Similarly, instead of writing a y to the 4th and moving the 4 out front, I'll put the 4 out front. Because each letter, y, z, and w are in the denominator, those logarithms need minuses in front. And that would be the one-step expansion for that particular logarithm. One last one. If I gave you something like this, the log base b of x to the 4th, y to the 6th, z to the 8th, w to the 9th. I asked you to expand that. That also would expand into 4 logarithms. So I'd make a 4 in front of the x logarithm, a 6 in front of the y logarithm, I would write a 4 in front of my x logarithm, a 6 in front of my y logarithm, an 8 in front of my z logarithm, and a 9 in front of my w logarithm. And then I need to put signs in. First logarithm never gets a sign. The rest of the logarithms will only pick up minus signs if their letters are in the denominator, because there's no fraction here, there's no denominator, there's no minuses that are necessary, and each of the logarithms are going to get pluses in front of them. So this would expand to 4 times the log base b of x, plus 6 times the log base b of y, plus 8 times the log base b of z, plus 9 times the log base b of w. So this is, in practice, what I do. So that last problem that I expanded, when I looked at that problem, I should have just said, well, I'm going to make 3 logarithms. I'm going to make the log base 7 of x, a log base 7 for y, a log base 7 for z. The z needs to have a 3 in front of it because it has an exponent of 3. Because both the y and the z are in the denominator, they get minus signs in front of them. The x being in the numerator gets no sign. Something written first gets no sign. If I look at that compared to the answer that I have, it's identical. I didn't actually finish the problem. I didn't put the 3 out front. So the answer that I had written on this, although it was correct, it didn't do the last step of the simplification, that being making the exponent into a coefficient. Similarly, this problem, if I was expanding it, I'd write 3 logarithms, one for the x, one for the y, one for the z, put the 3 in front of the z logarithm, and the only logarithm that picks up a minus is the one from the z because it's the one in the denominator. So in general, if we're asked to expand logarithms, we want to write as many logarithms as there are letters. We generally want to make exponents in front of logarithms, and the signs that you get, you only get minuses in front of letters or logarithms whose letters are from denominators. 20 is a harmless little problem. Just wants me to expand this. There's only 2 letters. I'm going to get 2 logarithms. So I'm going to get a log base 3 of x, a log base 3 of y. The x needs to have a 2 in front of its logarithm because of the exponent for the x, and because there's no division, there's no need for a minus sign, I just get a plus sign. The answer to 20 is just going to be 2 times the log base 3 of x plus the log base 3 of y. Nothing else to do. The next couple problems have fractional exponents, or radicals, and we have to know that if I see a square root, square roots are the same as 1/2 powers. If I see a cube root, which I'm not sure if we're going to run into one of those, but if I see a cubed root, I'm going to change those to a 1/3 power. So for problem number 22, before I expand this, I'd probably rewrite the problem as y and then make z have a 1/2 exponent, because square roots are equivalent to 1/2 power. And if I'm expanding, if I don't see the exponent that's implied, I won't get the right expansion. So this one needs to be expanded. I'm only going to get 2 logarithms because there's only 2 letters, one for the logarithm y, one for the logarithm z. The base stays 4. The exponent of the z that was in hiding or implied by the square root, that 1/2 is going to go in front of the z logarithm. I don't get any minuses because there isn't a fraction, so in front of the z logarithm I get a plus. And that would be the expansion for number 22, the log base 4 of y plus 1/2 the log base 4 of z. Last one has a fraction, which means I need to pick up a minus, but I also need to write the 1/2 power and 1/3 power that are implied. So this is really the log base 5 of x to the 1/2 over y to the 1/3, because square root is the same as 1/2 power, cube root is the same as 1/3 power. Now I can do my expansion. I'm going to expand this into 2 logarithms, one log base 5 of x, the other a log base 5 of y. The x gets a 1/2 exponent in front of it because it has, the x gets a 1/2 in front of it because of the exponent. The y gets a 1/3 in front of it because of its exponent. The y, because it's in the denominator of a fraction, gets a minus. So that's one group of problems. The last group of problems is going in reverse. And going in reverse for me is easier than expanding, but maybe it won't be for you. Hopefully it is. So each of the problems between 25 and 36 have 2 or 3 or 4 logarithms, and I'm supposed to write something that has 1 logarithm that's equal. And I can do this in multiple steps, or I can do it in 1 step. In multiple steps, the first thing you would do is make any multiplication into an exponent. My goal is to take this problem that has 3 logarithms and write something that's equal to it with 1 logarithm. And the beginnings, if you're doing this step by step, is to use the rule that makes multiplication into exponents. Now I can make these 3 logarithms into 1 logarithm, and I have to decide if I need a fraction or not, and if I need a fraction, what goes in the denominator of the fraction. You only need a fraction in your logarithm if there's a minus. Since there isn't a minus, I'm not going to have a fraction. And the x to the fifth, the y, and the z cubed are all just going to be multiplied. And it probably would be nice if I put this in a parentheses, but I certainly wouldn't take points off if you didn't. That's the answer for 26. That's rewriting the logarithm expression that has 3 logs, something that's equal with 1 log. And I did it in 2 steps, but probably could have done it in 1 step. Same sort of deal if I wanted to do 28, if I wanted to take 28 and write it as something that has 1 logarithm that's equal to it. If I was doing this in steps, the first step would be to use the multiplication, the exponent rule. And now I'm going to make the 2 logarithms into 1 logarithm and get my answer. The base stays 10. And this logarithm needs a fraction because there's a minus. The thing that goes in the denominator of the fraction is the y cubed because its logarithm has the minus in front of it. And that would be the answer for 28. It condensed the single logarithm that's equal to the original 2 logarithms is the log of x squared over y cubed. Same deal. If I wanted to do this in steps, I would make the first logarithm have an exponent of 4, the second logarithm have an exponent of 2, the third logarithm have an exponent of 3. I could take 2 steps to get from this step to the answer, but I'll just do it in 1. I'm going to take these 3 logarithms, write them as 1 logarithm. Because I see a minus, I know I need a fraction. If I didn't see a minus, I wouldn't have a fraction, but I do. I have to decide what goes in the denominator of the fraction, and then everything else will go in the numerator. The only letters that go in the denominator are those whose logarithm have a minus in front of it, and that's the z. So both the x and the y will wind up in the numerator. So the log of x to the 4th y squared over z cubed is the answer to problem number 30. 32 is written in a funky order because the minus isn't written last. I don't know that it makes a difference, but if you like to see the minus written last, it's not a bad thing to do, but it's absolutely not necessary. But I could write the minus last if that helps me, but I don't have to. And then I can make the 2 and the 4 into exponents. And now I can make the 3 logarithms into 1. I need a fraction because there's a subtraction. The only letter that goes in the denominator of the fraction is a letter whose logarithm has a minus in front of it, so that's the y. Both the x squared and the z are going to wind up in the numerator. So that would be a correct answer for number 32. 34, again, if it bothers you that it's not written in such a nice order, because the subtraction is written first, you can write the subtraction last. You have to do it correctly. No exponents to create because there's no numbers in front of the logarithms. I'm going to make the 3 logarithms into 1. Because there's subtraction, I need a division. If there wasn't a subtraction, I wouldn't make a division bar. The only letter that goes in the denominator is the x because it's the only letter whose logarithm has a minus in front of it. And that would be a perfect answer for 34. And then 36. Again, I could write 36 in a better order. I could write it as, the ln of x to the 4th plus the ln of z to the 5th minus the ln of y squared by writing the minus last and making the exponents and coefficients. And now I could make 1 logarithm. Any logarithm that has a minus in front of it is going to go in the denominator. I feel obliged to do just 1 more, even though I'm technically done. Let me sneak this in here. If I had something like this, 3 times the log of x minus 2 times the log of y minus 4 times the log of z. If that was the problem, I could make this the log of x cubed minus the log of y squared minus the log of z to the 4th. So this is not a homework problem. This is just an extra problem because I didn't have one like this, and I know this might come up. This, if I'm condensing it into one logarithm, I write the one logarithm, make a fraction because I see minuses. Both the y and the z would wind up in the denominator because both of those logarithms have minuses. So when you're condensing from multiple logs into one log and there's minuses, any logarithm that has a minus in front of it, its letter goes in the denominator. So for this particular one, this is the only one that has two minuses in it. There's going to be two letters in the denominator. All the problems that I've done so far only had one minus. There was only one letter in the denominator, but it's potential when we get to the review or in the homework even that you get something that comes up like this. Just so you have to just make sure to get the letter at the right level of the fraction. All right, so hopefully that was reviewed for you and it was a nice friendly section, and even if you had forgotten it, you remembered it quickly.